This is a relatively short video on the special properties of eigenvectors of symmetric matrices. After viewing this video, you'll be able to you'll understand what those special properties are, and you'll be able to confirm them for some example symmetric matrices. So remember that a symmetric matrix means that if A is symmetric, then it's equal to its transpose. So there are something like 4 theorems I'm going to cover. And this is covered in section 11.3 of Greenberg. And the first is that the eigenvalues of symmetric matrices are all real. In general, a matrix that's not symmetric could have real or imaginary eigenvalues. Remember, to find the eigenvalues, we had to take the determinant of A minus lambda times I, and that determinant led to an n-order polynomial, and it's possible for those eigenvalues to be real if the matrix is not symmetric. But in this case, the eigenvalues are always real. The second theorem states that if an eigenvalue, say lambda, is a multiplicity k, that is, it has it's repeated k times, the corresponding eigenspace spans k dimensions. In other words, the eigenvectors are linearly independent. So they'll be, if lambda is repeated k times, there'll still be k eigenvectors associated with them, but because they're linearly independent, they'll span k-dimensional space. And related to that is theorem 11.3.4, I'm going to skip one, is that if A is n by n, then its eigenvectors span n-dimensional space, and form a basis for that space. In other words, all the eigenvectors of a symmetric matrix are linearly independent and therefore span n-dimensional space, and therefore could be used as a set of base vectors for all the vectors in that space. And then last is theorem 11.3.3, which states that the eigenvectors corresponding to distinct eigenvalues are orthogonal. So of the distinct eigenvalues, the vectors associated with them are each orthogonal to one another. And Greenberg gives a very nice proof of this last theorem on page 555. And I encourage you to look through that. It's pretty elegant and not too long to look at, and I think it'll help your understanding of matrix manipulation and matrix math and the manipulation of matrix math. So that concludes this video on symmetric matrices. And in fact, these matrices come up quite a bit. Symmetric matrices are very common, for example, in continuum mechanics, fluid and solid mechanics applications. So if you get into those sorts of fields, you'll be dealing with these symmetric matrices that have these very nice properties.